I'm starting a new series on systems design on YouTube. What we are going to discuss in this series is different concepts related to system design, various tech blogs. And the blog which we are discussing today is how Discord stores billions of messages. I think this is a pretty popular blog because here they describe in quite detail the issues they faced with their database choice, and they had to move from MongoDB to Cassandra. What were the problems they were facing and how did they resolve them? So it's always good to learn from others' experiences, and I think this blog is definitely a good read. So I'll link the blog in the description so that you can go and read yourself. And what I'll do in this video is just go over this blog, kind of have a discussion with you, what I liked about this, what was interesting to me. I want to just give a disclaimer here that I am not super expert at systems design or at databases. I am just learning, so if you want to learn along, if you want to get involved in the discussion, you can watch this video and maybe we can discuss more in the comments. And you can also suggest me various other different tech blogs which you want me to create video on, and maybe we can learn along together in this process. That's the aim of this series. So let's dive right into it. So this blog is written in 2017 and it says that Discord continues to grow faster than we expected, and as of this blog post they have reached well past 120 million messages, and they want to store all the messages, all the chat history forever. They want to delete they do not want to delete the messages, and that's where the MongoDB kind of failed for them. So they said that the original version of Discord was built in just under 2 months in early 2015, and like for a quick iteration, for a quick product, they just went with MongoDB, but they knew that MongoDB would not serve the purpose in longer term and they would have to shift at some point of time. So around November 2015 itself, they already reached 100 million stored messages, and at that point of time, index that they were storing in the RAM was no longer able to fit in the RAM. And since the index was no longer in the RAM, the latencies started increasing, and then they decided to migrate to a new database. So for those who do not know what index is, so index is a particular data structure, usually like maybe a B tree or something, and you can create that data structure based on a particular, let's say if it's a SQL based database, you can create that data structure based on a particular column, and if you query that table based on that column, then it's a lot quick to query that because it is easy to traverse through that B tree, and index would then point to the actual entry in the table, and that's why querying on the index becomes faster, because traversing a B tree is faster than potentially going through all the entries sequentially in the table. So I just quickly looked up for how indexing is implemented by MongoDB. They say that MongoDB defines an index on a per collection level. Collection in a non-SQL database is just like a table in relational database, and you can create index on a single field or on multiple fields using a compound index. And they also say that MongoDB also use a B tree data structure for their index. So that's a brief side note on indexes. So coming back here, so the index could not fit in RAM, and if the index is no longer in the RAM and it's on the disk, it was increasing the latency because now you have to fetch the index from the disk, and also the things started to become unpredictable. So it was time to migrate to a database more suited to the task. So in here they mention the criteria about how they choose the right database, what were their requirements. So they mentioned that For their use case, the read to write ratio was about 50-50. So they were 50% reads, almost 50% write. They have different kind of channels. For the large public channels, the servers had to send a lot of messages, thousands of members sending thousands of messages a day and easily rack up millions of messages a year. For private channels, it was around 1 million messages a year, and there were servers which were serving voice chat, and these servers were only serving around 1000 messages in a year. But although the messages amount was small, these queries were resulting in many random seeks on the disk, and that's why it was a heavy operation. And they knew that they would be adding more features to Discord, and those features would lead to more random reads, and that's why they want the next database to serve the ability to do random reads more efficiently. So they laid out their requirements. Basically, they have a small team. I think at this point they only had 4 to 5 engineers. So they wanted a low maintenance database server, so they don't have to worry too much about it. They wanted something which could self-heal as much as possible, and they wanted scalability so that they do not have to reconsider the database solution later on. And finally, they wanted something open source. So Cassandra was the only database that fulfilled all of our requirements. It's what they say. So they give examples of large companies, Netflix and Apple, using thousands of Cassandra nodes, and they say that related data is stored contiguously on disk, providing minimum seeks and easy distribution around the cluster. So the Cassandra, it's kind of a key value store, so they call it as KKV store, where the first key determines the partition. So partition can refer to which shard your data is stored on if you are doing sharding, and which partition within a particular server if you are doing partition on a server level as well. So the way partitioning works in MongoDB is that, so basically MongoDB splits the chunk whenever they grow over a particular size, and they say that both inserts and updates can trigger a chunk split, and after splitting the chunks it uses some manual or automatic process to distribute those chunks evenly among all the shards, all the different servers. So the first key determines the partition or the shard where the data is stored. The second key determines the row within a collection, and then value is basically the data that we want to get. So here they describe that the first approach that they chose for sharding was to choose channel ID as your sharding mechanism. So basically store different data. So store the data of different channels in different shards or different nodes. But the problem was that as the channel grew big, the data for a particular channel, as it grew more than 100 MB in size, so Cassandra started giving a warning. So according to Cassandra best practices, a shard size should not be more than 100 MB. So partitions were found over 100 MB in size, and although Cassandra advertises that it can support 2 GB partitions, but it does not recommend it because it puts a lot of pressure on garbage collector, and since Cassandra is based on Java, I think a shard over 100 MB size puts a lot of pressure on the garbage collector of the Java underneath. Also, it created the issue of not having your different partitions of almost the equal size, which would be a poor load balancing practice. So that's why they realized that we have to somehow bound the size of the partitions and try to keep them always almost equal, because some Discord channels can exist for years and some of them might grow very big in size, and that's why they would not be able to fulfill this requirement of a particular shard size. So that's why they decided to shard their collections based on time, rather than based on a particular channel. So they introduced a new field called as bucket in their database. Bucket was kind of a timestamp, so you can say that a message would be stamped with bucket 1 for the first 10 days of messages, and then it would be stamped with bucket 2 for the next 10 days of messages, and you can add logic for that. So they added some logic to derive the bucket number using the timestamp, and so they added this bucket in their partition shard ID. So now basically they were sharding both on basis of channel ID as well as bucket. So for every channel, they divided every channel into various buckets based on the timestamp, so that if a particular channel grows very large, it would create a new bucket for that channel, and then it would be stored in a new shard accordingly. And so their entire primary key to fetch a content was first to use channel ID and a bucket to go to the relevant shard, and then use the message ID to get the actual content of the message. So to fetch the messages for a particular channel, they go to that particular shard, they go using the channel ID and few recent buckets for that channel. Then they check if they have collected enough messages in those buckets, and then they just render them if even enough messages are collected. Otherwise they can look for previous buckets in that channel. So the only downside of this was that it might be possible that for some channels there is not much activity over time, and since their shards are based on channel ID and bucket, and this bucket is based on time, so you might get a lot of buckets, but there is like not too much content in those, and so you have to traverse a lot of buckets to get the required number of messages to show. So that's what they mentioned here, that the downside of this method is that rarely active discords will have to query multiple buckets to collect enough messages over time. But they said that's fine because most of their Discord channels are quite active and they do not have to face this problem a lot. So they decided to go with Cassandra, and as an initial setup, to be on safe side, they started using both MongoDB and Cassandra, so that once they are confident with Cassandra, they can fully switch over to that. But as they moved to Cassandra, they faced a weird issue, and the issue was that some of the messages had their author ID as null, although author ID were not even allowed to be null. So they were confused, like what's happening in our database. So author ID was null because Cassandra follows a eventual consistency mechanism, by which we mean that when we write something to a database, so the database writes that message to few replicas, not all of the replicas, and when we read from the database, the data is read again from few replicas, and it is checked if the data is consistent between those two replicas, whatever few replicas it rendered it from. And from those few replicas, if it is same, then it just passes that information back to the client. But if it is not same, it checks that among the two replicas, among the two sources of truth, which one is more recent, which one has a new recent timestamp, and then it just takes that as the source of truth. It says that this is one I'm gonna go with, and they just update the older one with the new one. So this is known as last write wins. So let's quickly see what last write means. So if you haven't checked this book, please go and check this book out, Designing Data Intensive Applications. I'm gonna refer this book to read more about last write wins. So it says that even though writes don't have a natural ordering, we can force an arbitrary order on them because we can attach a timestamp to each write, and during the read we can pick the biggest timestamp and discard any other writes with an earlier timestamp. And this conflict resolution during the reads, like if we are reading from multiple replicas and we have a conflict among them, we can resolve that conflict using this approach, and this approach is called as last right wins. And this is the only supported conflict resolution method in Cassandra. It also mentioned this is not a very good approach, because if there are several concurrent writes to the same key, even if they were all supported as successful to the client, so client might think, yeah, my write has been done, but eventually only one of them would survive and other would be silently discarded. So there are some complications with this policy which they faced, and one of the examples they have shown is here. So let's say this first user wrote the data 1 stan hello, so stan is the user here, and someone deleted this entry, so it became all null, and he updated the message from hello to hello 2. So for the author, the most latest recent entry for the author was null, because this second guy updated it to be the null, but for the other two fields the most recent entry was hello 2 and 1. So that's why they were getting a null author when it was not even allowed, because of this last right win policy on a higher surface. So the way they solved this problem was that they checked the author ID, which is a required column, and they deleted the entry if the author ID corresponding to that was null. So the problem with deleting in Cassandra is, since it's eventually consistent, it cannot just delete the data like as soon as you ask it to delete the data, because it might delete in the data from few replicas, but then there would be few replicas where the data has not been deleted, and it will violate the eventual consistency. So to keep that information that this data was deleted, it marks the entry as a tombstone, which means it's gonna be deleted, but it's not been deleted from all the replicas. And you can configure that time amount when it would be deleted from all the replicas, and that time amount is 10 days by default. So the problem with this is that if you have a lot of tombstones, then you have a lot of data stored in your database which is not useful, which is deleted, which is marked as deleted, but every time you read from the database, it has to load all that data into the memory and then discard the tombstone once, because it's still there. It has been marked as tombstone but not removed, which is kind of inefficiency during read time. As they have described on read, it just skips over tombstones it come across. And one of the funny issue they mentioned this was that some people, what they did was that they created a channel with millions of messages. So they deleted everything from that channel but left one message, even though they deleted it. So even though they deleted everything from the channel except one message, but the messages in the database were stored as and marked as tombstone, and when you try to retrieve the messages of that particular channel, the server would have to go through all those messages and find out the message which is actually not deleted. So as they describe here, that it became obvious that they deleted millions of messages using our API, leaving only one message in the channel. And when a user loaded this channel, even though there was only one message, Cassandra had to effectively scan millions of message tombstones, which was generating a garbage faster than JVM could handle, and that was causing serious issues for them. So to solve this problem, they decreased the lifespan of tombstones from 10 days to 2 days, which means that now all the tombstones would be deleted after 2 days. So basically the things marked as tombstones would be deleted from all the replicas in 2 days. Also, they added some mechanism to keep track of empty buckets, so that let's say on the first query it went to all the buckets and it realized that some of the buckets were empty, it marked them as empty, and on the next query it does not look into those buckets at all. So they add some logic for that. So this was quite a funny problem, and I think it's quite a good read to read all through that. And then finally in the blog they just mention what are their future plans. They plan to move from Cassandra 2 to Cassandra 3 because the new storage format there can reduce the size by 50%, and in the long term they want to figure out how to archive unused channels if they wish to. I found this blog quite interesting. It's quite a popular blog. Do give it a read. The link to the blog is in the description of the video. Let me know if you like the video. This is my first video discussing a system design blog. I wish to create more of these, but I want to get the feedback. Should I create more of these, and if yes, provide me links to the relevant blogs which I can discuss in future videos. And I hope you like this. If you like this, give a thumbs up, subscribe to my YouTube channel, and see you in next video. Thank you so much.